All right, so good morning, everyone. And let me start by thanking the organizers for this invitation. And it's always a pleasure to be at ICTS here, although it's not physically possible to come here so often. Yeah. All right, so I'll be talking about primordial black holes from inflation and its various imprints in terms of whether they can be the candidate for the dark matter, whether they can also induce associated imprints, which we can observe or constrain using the existing as well as the upcoming observatories. For example, something called the induced gravitational waves. And there are also very nice set of imprints from the Hawking evaporation of these primordial black holes. I'll talk about each of these subtopics one by one as I go in the talk. Oh, this will not work? Okay, now it will work. All right. All right, so the outline of the talk is as follows. I'll start with a very brief discussion of why do we need to consider primordial black holes as an so-called the exotic candidates for the cold dark matter in the universe. And I'll provide some introduction about various mechanisms, and will focus on the inflationary mechanisms, which turn out to be very interesting, in particular to produce the primordial black holes as dark matter candidates in different mass ranges with possibly the entire abundance of dark matter in terms of PBH. And I'll talk about then how to compute the so-called the primordial scalar power spectrum, and talk about the constraints on the large scales that you need to always impose, because as we know that CMB puts very stringent and very strong constraints on the large scales on both the amplitude of the spectrum as well as the tilt of the spectrum. So these two numbers, so-called the AS and NS, is something that we cannot mess around with. These are fixed for us. But at the same time, we need to worry, or we need to ask the question that keeping these constraints fixed, what kind of scenario will give rise to primordial black hole formation on so-called these smaller scales, okay? And then I will talk briefly about how to compute the so-called the PBH mass fraction using so-called the Press-Schechter formalism. Then I will move into the second part of the talk, which will be on the observational imprints of primordial black holes. So it turns out that any mechanism, in particular the inflationary mechanisms, which do generate primordial black holes, also inevitably induce a secondary background of gravitational waves. So this is in addition to the primary background of gravitational waves, which comes from the primordial quantum fluctuations of the spin 2 degrees of freedom during inflation. This is an induced background, which is coming from the second order contributions from the scalar fluctuations. And this is mostly on the smaller scales, on the scales on which the primordial black holes are generated. And then there are very interesting imprints that we have recently worked out arising from the Hawking evaporation of these black holes. So you can assume that as soon as the black holes have been formed, they will start Hawking evaporate, okay? And then depending on the mass of the black holes of these PBH, you can find out the time or the duration within which a given mass PBH would either be completely evaporated or not completely evaporated. And then it turns out that there are distinct classes of imprints of these different mass PBH, the ones which have completely been evaporated, let's say by the BBN epoch, so-called the very ultra low mass PBH, which is around 10⁹ grams or so, while the other ones which could still survive the entire evolution of the universe and which could still be existing until today, they could be the ones which are more massive, of course, are the ones which would be the candidate for the cold dark matter. So I'll discuss some of these imprints that we have recently looked at, and I will summarize. So this is what we know about the universe, and this is something that we have been looking at, not just during this conference, but this is our broader understanding of the universe, that the universe starts from an inflationary phase, okay? We'll not talk about the singularity here. It starts from an inflationary phase, which is required for various reasons, for instance, to solve the horizon problem and flatness problem. But more importantly, this inflationary phase in the very early universe also, because it is typically driven by a scalar field, a fundamental field, the intrinsic quantum fluctuations of these fields give rise to the anisotropies in the CMB, which is around at this epoch, around 400,000 years from the Big Bang. And this is something we have observed very precisely. And there's a lot of information. This is what you call as the snapshot of the universe at that particular epoch. Okay, and this really gives a lot of information at this epoch, more importantly, because you can probe the universe being here today all the way back to this epoch. But the universe is opaque thereafter. Okay, therefore, you cannot, by means of any direct observations, you cannot probe it further. Therefore, this era or this epoch or this instant at which you have this snapshot of CMB fluctuations actually gives a lot of information about what had happened before this epoch. And this is what people have used, we have used as the community to understand and constrain the physics of the very early universe, in particular during the inflationary epoch. And as we know very well that very simple models based on single scalar fields, for instance, are the ones which are very much consistent with the observations. And this indeed is this measurement of these fluctuations in the temperature and isotropies in the CMB field is what can be used to constrain, as I mentioned, the amplitude and the tilt of the primordial spectrum that you can get from a particular inflation model. And thereafter, of course, there's something called the dark ages, when nothing much happens during the evolution of the universe. At some point, the first stars are formed, and so on and so forth. And this is what our picture is today, that you have lots of galaxies and lots of structure around us. And we can do lots of measurements today, as I said, to probe this entire duration or the entire part of the universe, but we cannot really go beyond that. And the age of this universe that we sort of estimate, again, from this epoch of CMB decoupling, because from this epoch only the photons start traveling freely to us today as an observer. And this age of the universe is estimated to be around 14 billion years. So this is what we have as our current understanding of the universe, as the timeline of the universe that we know. And then you talk about what is the best model which describes the data. Okay, and Anjan was talking about the lambda CDM model. And it turns out that lambda CDM still is the best model. Okay, of course, there are anomalies, there are tensions, there are outliers you need to worry about. But lambda CDM still is the best bet, in the sense that this is the simplest model, which is only described by 6 parameters. Okay, but more importantly, this analysis of the CMB data also tells you the constituents of the universe. Okay, in the sense that, as Anjan was talking about, if you think of the universe being flat, you impose this the sum of all the energy components being equal to 1, and then some of them are directly measured parameters from observations, and some of them are inferred. So keeping lambda CDM in mind, you find that a large chunk of this cake actually is dark. Okay, there's about 27%. Of course, these numbers have changed a little bit before and after Planck, but broadly speaking, only this 5% of this entire composition is what we know. Okay, rest of it, which is around 27% of dark matter and around 68, 69% of dark energy, is something we don't know. We do know that they exist because we have indirect evidence of their existence, but we don't really know what they are. What are the candidates? What are the fields? What are the particles? Or a cosmological constant? What are the candidates for explaining these dark components? Okay, so Anjan already talked a lot about this biggest fraction or the biggest, constituent of about dark energy. I'll focus on this part, dark matter. And as you know, as I said already, that there are evidence, different observations, okay, whether you take the rotation curves or CMB or bullet cluster, there are a variety of observations which do indicate the presence of dark matter, but we don't really know what is dark matter, what is the candidate, what is the particle which is responsible for dark matter. So with this, you can think of various candidates of dark matter, and you can broadly divide them into, let's say, a particle-like candidates, okay, which are sort of here, okay. People have also used modifications of gravity to explain the dark matter-like behavior at various scales. And more importantly, people have also looked at so-called the macroscopic objects being dark matter candidates. One thing you would immediately notice is that if dark matter is a particle-like candidate, there is no particle within the standard model of particle physics that can be the dark matter, which means you need to go beyond the standard model. So if you want to have, let's say, WIMP-like particle or any other particle-like candidate of dark matter, it has to be beyond standard model, okay? So if you can have observations which are probing, let's say, nature of dark matter in one way or the other, you are also indirectly probing the BSM physics, which you are also trying to probe in the colliders, okay? So the cosmological observations provide this interesting and, complementary avenue to probe the nature of dark matter, because there's nothing but the BSM physics. So as I said that there are these also macroscopic objects which have been proposed as the candidates of dark matter. And of course, if they are massive objects, there ought to be constraints. There ought to be observational constraints, okay? Because if you have a distribution of these macroscopic massive objects in the universe, it is going to show up as some signal, like in gravitational lensing, for instance, okay? And of course, there are various constraints on how much of these candidates could be in terms of dark matter. So before I go into the constraints, let me just provide an answer to the question which I put up in the outline, is that why do we need to consider primordial black holes, okay? They are certainly a very novel candidates for dark matter, and more importantly, thanks to the recent LIGO observations, not so recent, 6, 7, 8 years ago, they actually have turned out to be a very interesting candidates, okay? In fact, the very first paper about PBH being dark matter, or the mechanisms of producing PBH, was by Novikov, I believe, back in the days. But then there was really no activity in this field for a long, long time. So only with the LIGO observations, there's a lot of interest in the community to reconsider PBH as dark matter candidates. And as I said that, and I will go in details about how inflation can generate these primordial black holes. They are non-baryonic, they are non-relativistic, and they are nearly collisionless, okay? So that is also a very interesting, unique property of these primordial black holes. And there's indeed no new physics required, okay? I will explain that within simple models of inflation, keeping the CMB scales to be consistent with the observations, you can still produce abundant fraction of primordial black holes. And as I said that some of these candidates from LIGO observations have also indicated that the seeds of these supermassive black holes that have been observed in the observations could arise from the PBH being the seeds at very, very high redshifts. So there's a lot of interest, not just from the dark matter perspective about PBH, but also to explain various observations. So these are the constraints that we presently have. These are the latest constraints. And what I'm plotting here is the fraction of PBH in terms of dark matter, this omega being the dimensionless energy density parameter, as a function of mass of the PBH scaled by the solar mass, okay? And as I said, there are these bunch of constraints which arise from gravitational lensing, microlensing, and so on and so forth. And there are also constraints arising from the Hawking evaporation. As I said that, given the age of the universe, and we already know how black holes do evaporate, you can find out the constraint on the mass of the black holes, which would be completely evaporated by today. And therefore, those PBH cannot be the dark matter candidates because they have completely evaporated by today. So that puts this sort of bound over here. So if you look at all these constraints, it turns out that there are still these two rather narrow windows, which is around 10 power 17, 10 power 19 grams or 20, 22 grams, which is broadly around so-called the asteroid mass range. The PBH formed in these mass ranges can be the entire dark matter, because this is the fraction, okay? You can have a contribution arising from PBH, which could be the entire dark matter to particular mass range.
White dwarf, like burst from the eating of PBH?
It's like the white dwarf eating up something, a companion star, and bursting. Yes. But these constraints are very dynamical. They keep on changing. So if you look at different papers, these constraints are slightly different. All right. So this is the mass range that one is interested in if you want to have PBH as the entire dark matter. However, inflationary models in general can also produce PBH on the higher mass range as well, which are still useful. For instance, as I said, to understand or look at is for some of the evaporation signatures, as well as to explain some of the LIGO candidates. All right. So these are all sort of, I think this is updated, or maybe not. These are all the candidates which have been observed in LIGO. And because of this particular binary system that LIGO observed, people had actually speculated the possibility and discussed a lot that the LIGO indeed detected dark matter. Okay. And I haven't seen actually many follow-up papers after this one. So this is, I believe, from 2017 or so, right? You might 2017, but I haven't seen many follow-up papers. Although the number of such candidates have increased with the later LIGO data sets. All right. So then you want to ask, the question is that, as I said that, given the age of the universe, you can find out what is the mass of the PBH that would survive until today, because these are the black holes you are interested in, for them to be the dark matter candidates. Okay. So it turns out that, you can find out this mass has to be larger than 10 power minus 17 solar masses, or around 10 power 16 grams, which can survive the age of the universe. Okay. And at the same time, let's say if in the observations you end up detecting a below Chandrasekhar mass black hole, okay, subsolar mass black hole, I would think that this would indeed be a smoking gun proof of the existence of PBH, because astrophysical mechanisms can only produce PBH which are larger, okay, around Chandrasekhar mass. If we end up detecting a PBH or just a black hole in future observations which is around or below solar masses, it must be a very, very strong indication towards the existence of PBH. All right. So this is a very quick, summary or a crash course on how do you understand the formation of PBH during inflation. All right. So what I'm plotting is this horizon, okay, which is decreasing during inflation, okay. And at some point, inflation ends, and you have this reheating epoch, and the standard radiation domination starts. All right. And what I'm also plotting is these length scales. So the blue one is corresponding to the larger scales, which are the CMB scales, and the green over here is a much smaller scales where you want to generate primordial black holes. So these larger scales, as we know, they leave the horizon during inflation in the CMB scales typically leave in the first 8 to 10 e-folds of inflation. These are really large scales, so they exit early, but they re-enter later. Okay, they exit early, this is time. They exit early, but they re-enter later. Okay, these are the scales that we are observing in the CMB, right? The largest scales possible. And of course, as I said, that we have very strong constraints on this, four decades of scales, which are probed by CMB. Okay, first, let's say 8 or 10 e-folds of inflation. However, there are all these smaller scales which are also leaving the horizon during the later epochs, okay, after that first 10 e-folds of inflation. Okay, remember, you need to have around 50, 60 e-folds of inflation to solve the horizon problem. CMB scales only probe the first 10 e-folds of inflation. What about probing the inflationary physics for the remaining 50 e-folds of inflation? Okay, that's where this idea of generating primordial black holes on these smaller scales, different smaller scales, which correspond to different mass, as I will show later, comes into picture and becomes very interesting. And it turns out that you need to have large overdensities. Remember, you want to form something out of a collapse. Okay, so you need to have large overdensities. These fluctuations that we're talking about over here should have very large amplitude. And when they re-enter the horizon, okay, they will collapse. Let's say during radiation domination, they will collapse and form a distribution of primordial black holes. This is the broad understanding of how you produce PBH in the first place. All right. And so this is another way of understanding it, is that what you are looking at is the density contrast. Okay. And only above a critical density threshold, that region will collapse and form PBH. okay? And this is given by delta C, the critical density contrast. But what you have is also a scale here, a comparison of a scale, which is what I showed in the previous plot, is that you need to compare the length scale associated with the PBH to the horizon, okay? So in this case, of course, and of course, now we are during radiation, okay? So 1 over AH, which I have compared with lambda, the physical wavelength, actually increases with time, okay? So you can see this with time, this region, which is 1 over AH, essentially increases. Okay, and when this is of the same order, in the sense when this mode has re-entered the horizon during radiation, this will collapse. And this particular mode, let's say, has a density contrast which is larger than the critical density threshold. So this density contrast is so large, this can actually overcome the radiation pressure. Yes, yes, yes. This is so large, it can actually overcome the radiation pressure and they can still collapse during radiation. All right, so this is how you understand that any fluctuation which has a density contrast larger than the threshold, okay, would when they re-enter during the radiation domination, would collapse and form these primordial black holes. So what you are interested in is essentially, if you look at this parameter space, what I'm plotting here is the amplitude of the so-called the density fluctuations or the curvature fluctuations as a function of the wave numbers, okay? And this part of the parameter space is well constrained, as I have talked about, okay? The amplitude being 10 power minus 4 minus 5, and these are the, few orders of scales in K that you have, very good constraints on. But what you are interested in is in this other part of the parameter space, okay? Which is on larger wave numbers or smaller scales, because lambda is 1 over K. And it turns out that if you want to produce large enough abundance, okay, let's say close to 1, if you want all your PBH to be the dark matter, okay, then this power spectrum, okay, has to be large enough. And of course, this number depends on what is your mass distribution and what is the critical density contrast. But this is a ballpark number that you have to keep in mind, which means any inflationary model that you are interested in for the purpose of producing primordial black holes, it is evident from this plot that while the power spectrum should be consistent with the CMB observations, you need to have a dynamics which gives you a large enough amplification of the power spectrum on these smaller scales. It depends on what scales you have the peak, okay? Because there's a mapping between K and M, as I will show later. So it really depends on the dynamics of your model and at what K you have a enhancement of power, that particular fluctuation will collapse and give you a particular mass PBH. All right. So there are a large number of, even within inflation and also beyond inflation, there are a large number of mechanisms which people have looked at for producing PBH. I have just listed the ones which are, which could be within the umbrella of inflationary mechanisms. Okay. There could be single field mechanisms. There could be, rise of power spectrum because of large spectral index. And keep in mind, all these constraints, when we talk about the tilt and the spectral index, or even, tilt and the running of tilt, is only on the CMB scales. Like Planck only gives you the constraints on CMB scales. But we do not have a priori any constraints on the smaller scales, right? The remaining 50 E-folds of inflation. So you can as well pick up your favorite model and have, have a rise in the power spectrum because of the running spectral index. And of course, there are other bunch of scenarios, including both single fields and multi fields and at different epochs and so on and so forth. There are really a very large number of models which people have looked at in the last couple of years. So I'll talk about a very simple single field model, which contains a point of inflection in its potential. Okay, and there are various motivations to have this kind of a potential, especially in the framework of effective field theory of inflation, that rather than having a monomial potential, you can have a polynomial potential. Okay, and as I said, that you only have constraints on the CMB scales, on the large scales. So if you have a plateau corresponding to CMB scales, also corresponding to the large field value of phi, we are still within the framework of so-called the large field inflationary models. Okay, so because this part of the potential is nearly flat, and again, this is just a sketch. Okay, you find that this allows for an initial slow roll phase, which is what you need to make your power spectrum consistent with the CMB. Okay, you need NS to be 0.963 or something, right? Very close to being scale invariant. So this initial slow roll phase will actually make the model consistent. Are you sure? With the data, okay? And of course, this dynamics, that's because you have a point of inflection, it will allow for violation of slow roll, thereby having something called the ultra slow roll phase. And I was briefly showed that the dynamics of these fluctuations is very, very different during this ultra slow roll phase. And eventually the potential will have a global minima, thereby having the final slow roll phase and also end of inflation and the reheating phase thereafter. All right. So this is a particular model that we looked at. As I said, it's a polynomial potential we looked at, and we found that this has this point of inflection, and this is also slow roll, although it may not be so evident from the picture, but it is also allows slow roll at the large field values of phi. Therefore, it is consistent with the CMB observations for the large scales, but it gives a very interesting dynamics on the smaller scales. All right. So I'll not go into the details of all these calculations due to the lack of time, but there's something very standard that you do in order to compute the power spectrum in any inflationary model. Okay, you look at something called the evolution of these curvature perturbations, you look at their solution in the super horizon limit when the modes are frozen, and you compute the power spectrum. And this also, to indicate that this is the epoch during which these violation from slow roll happens. Okay, this is the initial slow roll phase, and that's where the violation from slow roll happens, and that's where the interesting dynamics takes place. So this is what you find. You compute the power spectrum, let's say at the end of inflation, and you find that the initial part of the spectrum, which is corresponding to CMB scales, is nearly scale invariant. Okay, although I will briefly mention that there are the tilt is slightly larger. And then because of this ultra slow roll phase, because of the dynamics of this particular model, you get this huge enhancement on the smaller scales. And depending on the location of the inflection point, you can have this enhancement at different values of this wave number, which eventually will correspond to different masses of PBH. All right. Once again, I'll not go into this recipe of PBH, how you go from the inflationary power spectrum to the computation of the PBH mass fraction. This is very standard Press-Schechter formalism. And of course, there are some caveats to understand that the way you compute this fraction depends on many things like, what particular formalism you have in mind, choice of the window function, as well as the value of the density contrast. But more importantly, this is something to keep in mind that, because remember, we are forming the primordial black holes from the tail of the distribution. The density contrast has to be larger than delta C, right? Only when the magnitude is larger than delta C, you form a PBH. And therefore, if your primordial density distribution is not Gaussian, even if there are tiny amount of non-Gaussianities, this will show up very strongly in the tail of this distribution. And as a result, it has been shown that primordial non-Gaussianities very strongly affect the PBH formation, and they do play a very important role in the calculation of the abundance. But I'll not go into this part. So we can use this Press-Schechter and compute this mass fraction. And as I said, that these are the two windows in which you can have the PBH as the entire dark matter. And for certain values of the parameters, you find that you can have the entire contribution, entire abundance coming from primordial black holes. All right. And we found that in this particular model, there's a slight tension, especially when you go to larger mass PBH. Okay. Because as I said that the constraints that you have at the pivot scale from CMB on the primordial spectrum are only sort of respected for certain mass PBH, otherwise the tilt becomes larger. Anyway, and then we also looked at the effects of reheating, but I will perhaps not have time to go into the details. So this is where we are as far as the space is concerned. You have the primordial power spectrum, the 4 orders of magnitude are well constrained from CMB. And then there are projected constraints from, let's say, mu distortions and the corresponding gravitational waves over here. But there's still these, 20 orders of magnitude in K space, or so-called the 40-50 force of inflation, which still remains to be constrained. All right, so I'll go into the second part of the talk very quickly, and we'll talk about these induced secondary gravitational waves, which are inevitably generated in any scenario of primordial black hole formation. So this is the equation that you typically solve to understand the primary contribution, which is nothing but the quantum fluctuations of this spin 2 field during inflation, to compute the gravitational wave spectrum, all right? With the right-hand side being 0, okay? Because these are the vacuum fluctuations which are sort of excited during inflation, and that's what you are interested in. But in all these scenarios, because now on the smaller scales, your power spectrum is much larger. And therefore, the second order contribution, which is otherwise negligible on the larger scales, becomes relevant here. And this is what you are interested in. So essentially, you are interested in looking at the inhomogeneous solution to this particular differential equation for the tensor modes. Okay. Once again, I will not go into the details of all this, but this is something very standard. You want to solve this equation, and you want to look at the 2-point function of these induced modes, which is nothing but the power spectrum, and you can characterize it in terms of the energy density of the gravitational waves. Okay. Once again, these are details. I will not go into this. This is what I mentioned, that a particular scale, if it has large enough overdensities, when it re-enters the horizon, will collapse and form a PBH. And there's indeed a relation, okay, between the K that collapses, okay? And in all this estimation, we are assuming that the collapse is more or less instantaneous. Okay, of course, there's an efficiency factor you need to keep in mind, but otherwise the collapse is instantaneous. And for a particular K, you will produce a PBH for a particular mass. And eventually, this wave number is also related to the frequency of this induced gravitational waves that I will show in the next plot. And you find that for LISA, which is sensitive around the millihertz frequency band, you have PBH around this 10⁻⁻12 solar masses. All right. So this is what we find after we compute this induced gravity wave spectrum in these scenarios, again for the different power spectra that I showed, and you find this very nice, interesting IR growth, as well as the tail of all these spectra very similar to each other. And you can see that they sort of span a wide range of frequencies and can in principle be probed by more than one observatories in the near future. Right? And there's also a way to understand this IR growth of all these spectra. So what we have done is calculate everything numerically, but there are ways to also understand this IR scaling of the power spectra for the gravitational waves. All right. And also there are again imprints of reheating on this GW spectrum. In particular, if you have a metal-dominated phase, which behaves as the reheating epoch, then you can have so-called the secondary enhancement of this GW spectrum, although it happens to be at much larger frequency. It is not directly observable because there are no observatories in this particular part of the frequency domain. So I'll very quickly, in 2 minutes, I'll talk about the imprints from evaporation. Okay, so what is it that you want to understand? As I said, that these black holes, once they are produced, they should evaporate by means of Hawking radiation. Okay, and all this is something which is very standard, that for a Schwarzschild-like black hole, which is non-spinning, you can find out the temperature of the black hole in terms of mass, and this is inversely proportional to mass. Okay, similarly, you can find out the time scale during which the PBH will completely evaporate. Okay, and of course, it is evident that this is proportional to m cube. Therefore, the lighter black holes will evaporate quickly. The massive ones will evaporate in longer time. All these results are slightly different for the case of a spinning PBH. Okay, so the temperature of the PBH is affected like this, where this A star is this sort of dimensionless or the reduced angular momentum parameter, which is, so MPL is the reduced Planck mass. If you set it to 1, then A star is just J over m square. So this is what this parameter is, and this turns out to be dimensionless. And more importantly, for the spinning PBH, this time scale is also affected. Okay, so the spinning black holes will take a different time to completely evaporate as compared to non-spinning black holes. Okay, and this is what you can find out. And there's no analytical expression for these sort of the form factors. Okay, so what you need to do is that for these spinning black holes, you want to understand how the mass is changing with time because the energy is radiated away. At the same time, the spin also is affected because spin is not fixed. This A star is sort of like an initial spin. But as the black hole rotates and evaporates, the spin is also affected. And there are these two first order differential equations which characterize the evolution of both mass and spin. And once again, it's very difficult to understand the analytical solution for these equations, okay? But there are some classical papers by Don Page back in 70s who has really, worked out these so-called the gamma and the epsilon for different particles which are being emitted. But then these days, there are also some numerical codes available like Black Hawk, which can actually do the job for you. All right. So what we are interested in this context for the evaporation signatures is that we are agnostic about what produces PBH in the first place. We just assume that there are these ultralight PBH, okay? And as I made a comment in the beginning that we are interested for the evaporation signatures, the PBH which would completely evaporate by BBN. And this condition puts a constraint on the mass of the PBH. So mass around 10 power 8, 10 power 9 gram PBH would be completely evaporated by BBN. And these are the ones that we are interested in, okay? So you can think of by tuning the mass and the, the abundance, this beta is the fractional abundance, you can find out a situation in which the PBH would actually dominate the universe for a very short duration. So you want to understand the imprints of this PBH dominated epoch. And because PBH behaves like matter, we call it the early matter dominated epoch. It's not the conventional matter dominated epoch, which happens after decoupling. Okay, and you can compute this induced stochastic wave background that I had mentioned earlier. But there are a few things to note, few interesting things to note here is that, first of all, if you think of this distribution of ultralight PBH, because the inhomogeneous distribution, there are going to be Poisson fluctuations. These Poisson fluctuations are isocurvature because they are in the radiation background. These isocurvature can be converted to adiabatic, okay? And then they will give an additional contribution to the GW spectra that I showed earlier. This is precisely this resonant secondary peak is coming from in this picture. And we also worked it out for the two cases of completely non-spinning and these spinning black holes for these different mass ranges and the abundance. And you find that this can still, be constrained / detected with the future observatories. The next question we asked is that what other imprints are possible? So if you think of PBH evaporation and this evaporation containing all sorts of particles, you can think of, let's say, unstable heavy particles. If they decay due to a baryon violating process, they can induce the baryon asymmetry in the universe, for instance. If you think of the stable heavy particles from evaporation, they can be a dark matter candidate. And at the same time, if you think of very light relativistic particles, they can contribute to the so-called the effective relativistic degrees of freedom that you have already strong constraints upon from CMB. So this is what we worked out, that what is the contribution for these different mass PBH in terms of the delta effective. And you find that the contribution is different. I just want to highlight one point here is that if you want to produce a spinning particle, a spin 2 particle from the evaporation, okay, strongly. For example, think of a graviton. Graviton is a spin 2 particle, okay? So graviton background from this evaporation is not produced at all, or it is very, very subdominant, or a non-spinning black hole. However, if you want to produce this graviton background strongly, your black hole has to be a sort of a maximally spinning one. Then only you can produce these spinning particles out of the evaporation. And you find that there's this parameter space, which is sort of, for these backgrounds, which can possibly be constrained by the upcoming experiments, CMB-HT and CMB Bharat. I'll not go into the details, but I'm happy to discuss it after. And once again, you can look at the stable heavy particles. okay, from the evaporation, which could also be dark matter candidates. And you find these different contours for these spinning and non-spinning black holes. And there's a part of parameter space which is ruled out because we are always interested in the PBH dominated epoch. Okay, so you find that this is the allowed parameter space in which these stable heavy dark matter particles would be the entire dark matter. Okay, and we also looked at the sensitivities of the future gravitational wave observatories for a given SNR ratio, and we found that there's a parameter space which is still allowed if you put in everything together. Okay, so I'll not spend much time on this. I'll conclude. Primordial black holes are indeed very interesting and many different candidates for the cold dark matter. And as I said in the beginning, that they are really a very interesting probe of the small scale dynamics during inflation. Okay, inflation can in general produce the significant abundance of primordial black holes on different mass scales. And of course, the results have to be model dependent. Okay, there are interesting implications for future observatories. This induced gravitational wave background on these smaller scales, which are all the smaller millihertz frequencies, which is probed by LISA, DeSigo, and BBO, would be an interesting indicator of a background which is induced by PBH. Okay, and once again, you can twist the argument and say that non-observation of such a background by LISA may also rule out PBH as dark matter. And also, there are a bunch of these interesting imprints to dark radiation and dark matter from the evaporation, and there are also interesting constraints from future observation. I'll stop here. Thank you very much.
So we can have one or two very quick questions. Tathagata.
Okay. Okay.
But my question is about this PBH GW spectrum that you are getting.
Mhm. You mean here?
This one and also the last one, the next one you showed.
This
Yeah.
one? Yeah.
So why there is a shoulder before this peak frequency?
So the two peaks you can understand as follows. The first peak comes from the inflationary adiabatic fluctuations. Okay.
No,
The
that part you explained. But even before for the first peak also,
yes.
before the peak there is a kink right there.
Yes. I
So-
mean, there's no really a physical reason behind this kink because people have even computed for let's say a power spectrum being a delta function. They have computed the corresponding induced GW spectrum, and they also find a kink. I think this is a bit numerical. It has got nothing to do with being physical. But as I said, that you can understand this slope over here and this slope over here using some arguments. Okay, this is an exactly numerically calculated spectrum.
Thank you.
Well, thank you. It is very interesting. Would there be also signature, dynamical signature, perhaps at the solar system scale or such? Maybe even microlensing is probably very difficult, but or you think the primary signature will be with the gravitational wave signals? For this granular, due to the granularity of the
There
dark
may be,
matter on
let's
that-
say if you are producing
scale.
PBH and there's a distribution of these PBH, which are let's say everywhere. Okay. There could be some imprints I'm not aware of, but all these signatures that I have talked about is mostly, during the early epochs, CMB and the induced GW. But these solar system signatures, I'm not familiar. There might be some.
Okay, thank you.
So, yeah.
So what exactly is the number density of the primordial black holes that you're looking at? Because if you, in the parameter space where the entirety of dark matter is just these primordial black holes, wouldn't that mean something for the galaxy formation in dark matter halos? And wouldn't that lead to a lot of, different structures being formed?
Yes, lately people have been doing these N-body simulations with also the PBH being in the background. And I believe that also puts a constraint, okay? But I guess, because as I said that there's a relation between the K and the M, okay? in those regimes, when you want, sorry, maybe I should, here, okay? This range, if you translate it to the wave numbers, it will still not be relevant for the large scale structure. Okay.
How things look at a galaxy scale.
Yes. So, but if you are producing PBH, which are around the galactic scales, okay, I mean, in terms of the wave number, and if there's a significant abundance, it is going to affect. And as I said, that people actually have been doing these simulations recently to take this contribution into account.
Let's move on. If you don't mind, let's defer to the afternoon. So let's thank Rajiv again.